Okay, this is Viz 2320 Computing 2. This is the second video in exploring the Scipy module and looking at numerical Python, and in this video we're going to be talking about interpolation. So in the first video we used scipy.optimize to the fmin and fsolve functions to find minima and roots in continuous functions. So that's where you have a function which you can put any value of x you like and it'll return the value of the function at that value of x. The problem in physics is that we're often working with experimental data where we've measured it at discrete data points. So in general you've made a set of measurements, you know what value of x and y you've got, so you've picked some variable, you've set it, you've measured a data point there, you've got some value of y. The problem is you don't have a good idea of what the values were in between those data points because you didn't measure them. So this is where interpolation comes in. So interpolation is really just the process of estimating data values that lie between experimental data points. So on the right here we've got a set of data points we've measured, and the easiest thing you can do is you could think about drawing straight lines between those data points, and then if you wanted to guess a value that lay between those data points, it would lie on those straight lines. And you look at that and say, okay, that's fine, except of course you might well think, well, that thing in the middle there looks an awful like it's going to be some sort of peak, and therefore just drawing a straight line between that point and that point might well be a bit of an underestimate. And what you'd need to go and do is think about, well, how can I get out some sort of more peak shape around it? So you want to do something a bit like that to make it a smooth curve that joins up all the data points, and that'll naturally give you a peak, and that would then tell you that in fact the green dots were a better representation, a better estimate of what the data would have been had you done the measurement in between. So this is a useful thing to go and do if, for example, you need to take the difference between two sets of data that have been measured at slightly different values along the horizontal axis, so different independent values. So what you would then do is you'd use the interpolation to get everything onto a common set of x values, and then that would let you just do the subtraction straight away. The other point where interpolation is really useful is if you need to fill in missing data, or indeed when you've got to go and use some method that wants a continuously varying function, and you've only got discrete data sets. So this is why it's useful to know about this, because interpolation is a really handy thing to be able to go and do on your data. So in Scipy, interpolation is carried out by the scipy.interpolate module. It gives, again, loads of functions. So just to give you some idea, univariate interpolation means interpolating in one dimension, and multivariate interpolation is interpolating across 2 dimensions. Lots of different functions there, but the important ones, or the ones to start with, are the interp1d and the interp2d. And they both simply take your x data, your y data, z data if it's 2-dimensional interpolation you're doing, and then a kind, which can either be linear, which means you're drawing straight lines between the points, or cubic, which means you're trying to fit a cubic curve locally to each set of points to make a smoothly varying curve. And then what both functions give you is something that behaves like a function, in that you can call it with any set of x you like, so long as those x values are within the same range of the original x data you had. So the important thing here is that interpolation is not extrapolation. You can't go and say, well, I have this set of data measured in a certain range of x, what would it be outside of that range? You can only say, what would it be at other values of x I didn't measure, but inside the same range that I covered with my measurements. So you can't use this to extrapolate data. If you want to extrapolate data, then really you have to do some kind of local fit, or have some kind of fit. You have to have some idea of kind of how the data should be behaving and then fit to it. And that's something we'll come to in a later video. Okay, so let's go and actually have a look at some code then. So what we're going to do is we're going to work with a set of data points that I'm going to load in from disk. So I have a file here with a lot of data in it. So I have 100 rows of data, and I'm going to read it in. So I'm going to start off by importing NumPy and matplotlib, pyplot as usual. This is just the same as we've done in the previous videos in this series. And I'm going to use the NumPy gen from txt function that was covered in files 4 to read in that data. So that's going to get my data in as a two-dimensional array, and then I'm just going to pull out the second and third columns, which are my x, so a time, and y, which is a signal column. The first column is just a row number, which I'm not interested in. Okay, so I get my x and my y data, and we'll just plot it to start with so you can see the data. And then the final thing I'm doing on this line here is I'm creating a new set of x values which are in the same range. So the data I've got defines plus or minus 5. So I'm going to take the same, more or less the same range, but I'm having, rather than 100 points, I'm having 1001 points. So I've got clearly an awful lot more data points in there than I've got measurements for. Okay, so we'll just run that, and there's the data set. So you'll see again it's an oscillating function with some trend on it, and that's what we're going to try and work with. So the first thing we're going to do then is we're going to go and interpolate into create a description that shows how the data varies in the gaps. So what we can do then is we want to import the interp1d function. So we're going to let's create a linear interpolation first. I'm going to call that linear. And then onto the interpolation function. All it takes, you see if I bring the help up, is the x and the y. I'm going to set the kind equal to linear, and that's really the only things I need to set to get it to work. Everything else is optional arguments. Like so. And now what we can do, so linear is going to be something which is going to behave a bit like a function. So what we can do, well, let's just run that and we'll show you how it works. So there we go, we didn't need that plotter yet. So I said linear is an interpolation function. It simply takes in the x values and is going to give us a y value. So I could give it, say, 3.141. Actually, that probably is defined as a variable. Let's say 3.2. And it comes back and gives us an answer. And I give it any arbitrary value I want. And it comes back and tells us, again, what the value of that data set at that particular value would be. If I try asking it for a value that's outside the range, so say 5.3, it comes back and tells me it's a value error because I'm trying to ask it to come to look at outside the space of which the data was originally defined. So what we can do then is we can add to our plot let's make this a green line. So I'm just plotting this x2 variable, which is a set of extra data points, and the values I get from the linear interpolation. I'm going to give that a green line. If I run that, there we go. So we now have a green line. You see it's going smoothly through all the data sets. And if I zoom in, then it looks like a nice smooth curve, but you see that it's drawn straight lines between each data point. That's because I'm using linear interpolation. So you can actually see that it is actually done as a series of straight lines. So I've evaluated that straight line over lots of different points in between, which is how I can see that I've got line. You can see the line in between, but it is actually just a straight line section that goes from this point to this point, and so on. Okay, so obviously that's not brilliant if you've got sharply peaked data, so let's create a cubic interpolation as well. Where are we going? Interp 1D, X, Y, cubic. And then we'll do the same, we'll plot the cubic interpolation up. And let's do that in a blue line. And there we go. So it looks on the face of it like this green and this blue lines are actually sitting exactly on top of each other. But again, if we zoom in really tightly on the data, and there you can see that the cubic interpolation has drawn a smooth curve that goes through all the data points, whereas the linear interpolation has just joined them up with straight lines. So cubic interpolation in some sense you might think is giving you a better estimate of what's going on. Of course the disadvantage is that you are taking up more processing power, so it's taking you longer. So if you have particularly complicated data, then cubic interpolation is going to take you longer to do than just a simple linear interpolation. And you have to decide that, given you're estimating the difference between these data points, is that difference between the green and the blue line really important, really significant? So if each of these data points had an error bar, a big error bar on them, then you would think, well, probably it doesn't really matter that much whether it's cubic or linear, and so it might actually be better to use the linear interpolation. So this, of course, comes back to the kind of central point. When you're interpolating, you are estimating data, you're making things up, and so you need to have some idea that this is not necessarily the same thing as you might have exactly measured, and particularly if your data is not measured in a very dense grid, if you've not got lots of different data points, then who knows what's going on in between in a real experiment. So you always need to have that at the back of your mind. So the other problem with interpolation is what happens if your data is noisy. So let's just show you what happens if we have some noisy data here. So what I'm going to do is I'm going to make use of the NumPy random number generator to add some normally distributed, so Gaussian distribution data. Gaussian distributed noise, random numbers to my data. So I'm just adding a random number with a full width half maximum of 0.1 to that data set. So now let's go and see what it does. Okay, so first of all you can see the data set looks a lot scraggier because of that noise I've added. If we zoom in, then you can see again it's still doing the same thing. The green is joining straight line segments. The cubic interpolation is going and doing nice smooth curves like that. So you think, okay, that's fine. Right, so now imagine that we go and take these interpolation functions and we say, okay, tell me about where the minima or the maxima are. Now, if just by eyeballing this, you'd say, okay, there's a maxima there, there's a maxima there, and there's a maxima there, there's a minima here and here. You can work out the root there, 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 and somewhere around here and here. The problem is that if you're a computer, you don't have the power of the human brain to go and discard the random noise, and instead what you'll do is say, there's a maxima there, there's a maxima there, there's a maxima there, there's a minima there, there's a minima there, and you'll end up finding a lot of extra minima and maxima. And likewise, if you're looking for roots, then in this region here you can see, look, root there, root there, root there, root there, root there, root there, rather than just maybe the two roots that you might expect for given the amount of noise in the data. So the problem here is that interpolation is literally joining the dots. So what can we do about this? Interpolation just joins the dots. It's really bad if you're trying to find minima or maxima. Well, of course, the best thing you could do is to have some kind of physical model that you think is going to describe your data, which you could then fit to your data. And that's going to be the subject of the fourth video in this series. Your other option then is to use some kind of spline fit. This is also quite good if you just want to give a guide for the eye to a data plot. So often if you've got a set of data points you've measured, particularly if you've got lots of different data series on the same graph, it gets really confusing to keep track of which dots go with which dots, and it's very tempting to go and fit some kind of arbitrary polynomial to the data. The problem is, as soon as you start fitting data, you really need to understand why that particular function is being used. And if all you're trying to do is give a guide for the eye, just to say these data points are connected together because they're the same experiment or they're somehow related to each other, then often a spline is actually a much better thing to go and do. The only thing I'll say here, and this is me speaking as the convener of the Advanced Lab module, is that for goodness sake, do go and say it's a guide for the eye in your figure caption or when you're presenting the data. Okay, so how can we make a spline? So what we're going to do then is going to make use of the spline function. So if we just go back to the web page, then go down a bit on the Interpolate, you see you've got 1D splines, 2D splines, and we're in particular going to make use of this univariate spline function here to create a one-dimensional spline to define our data, because that's kind of the easiest thing to do. Okay, so univariate spline is what we're going to want to use, so we're not going to interpolate any longer, so I'll get rid of that. So let's create a spline, univariate spline, again x and y. So by default you can, well, a couple of things you can do. You can specify a weighting, so how important is it that your spline function goes close to a particular data point. So in real data, if you've measured some things with error bars, then 1 over the size of the error bar would give you a weighting. So the bigger the error bar, the less important it is to get your spline to go close to that data point. The smaller the error bar, the more confident you are that value is really there. So you could, if you have a set of error bars, you could feed 1 over the error bar in as your W. The other thing, however, is important, useful parameter are the K and the S. So if you've used Origin, you may well have come across using cubic splines. That's if you've got K equal to 3. You can set K equal to any value up to 5, so you can create binomial splines, or say cubic splines, or go up to 4th or 5th order splines. But cubic splines are often good enough. And the other thing then is S, which is a smoothing parameter. So an S of 0 will basically just interpolate, will join all the dots, and by default the S you're going to get is going to give you quite a heavy degree of smoothing. So we'll do that first and just show you what the default values give you. So we're going to plot again. So x2 spline x2. Let's have a we'll call it a blue line, shall we? Yeah. Okay. So run that. Okay. So the blue line is the spline. You can look at it and go, well, yeah, okay, but it's a bit too much smoothing there, really. It's you'd think, looking at this data set, that really the red, it has to have some sort of oscillation like that that's real. It's just this sort of crud like this is probably not real. So we've got a bit too much smoothing going on there. So what we do is we go into the spline. So I set S equal to 0, we'll go to the other extreme, and what it does is it's just like doing interpolation. So we want a small value of s, but not too small. So let's try, say, an s of 2. And you see that's looking an awful lot better. That's looking rather more convincingly that it's actually picking up the main features of our data, but not overemphasizing the noise in there. So roughly that's using is throwing away things where it jumps up and down just within a couple of data points. So in this particular data set, a smoothing of 1 or 2 tends to work quite nicely. And one can play around with it and see what different levels of smoothing you get. Okay. So then what I've been showing you in this then is the Interpolate module that provides interpolation and spline functions. In both cases you're creating something which behaves a bit like a function, but it's only defined within the range of the data you originally started with. So interp1d for 1D interpolation, and univariate spline giving you a smoothing spline again over 1D, and there are 2D or multiple D versions of doing the same thing.